Okay, ladies and gentlemen, today we're going to be working with the second fundamental theorem of calculus, which is stated below here, the integral from h of x to g of x of f of t dt. That is, if I was to take the derivative of this, I would get f of g of x times g prime of x minus f of h of x times h prime of x, okay? It's got to be the derivative of this integral is going to be equal to this, okay? So I'm going to walk you through this. We're going to do this in a more traditional, where we do the integral and then we take the derivative, versus kind of a shortcut using this second fundamental theorem, okay? It should not be any surprise that the integral, which we originally started out as anti-differentiation, that the integral is going to cancel out. We're going to be left with just f, right? This is not f prime or capital F that, you know, integrating is the antiderivative, and then you derivative it, and you get back to the same thing, right? Antiderivative and then derivative. So the only problem with this theorem is, where does this g prime and h prime come from? Why do we need to plug in and multiply by these bounds? So let's take an example where, okay, we can actually take the integral of this. I know how to do the integral from 5x to x squared of e to the 3t dt. Well, this is a u substitution problem, where you would have u being 3t, and then you'd have to, you know, take du, which would be 1/3, or I'm sorry, 3 times dt, and then fudge the 3. But you know, I kind of know that already, so I'm just going to say this is 1/3 e to the 3t. You can go ahead and check that out, and it's got to be evaluated from 5x to x squared. Okay, and so if we do evaluate it, we get 1/3 e to the 3x squared minus 1/3 e to the 15x. Well, now we need to take the derivative, ddx, of this answer. So derivative of 1/3 e to the 3x squared minus 1/3 e to the 15x. Well, the derivative of the first one is going to be 1/3 e to the 3x squared, because the derivative of e to the 3x squared is itself, but then we have to multiply it by 6x, right? We have to take the derivative of 3x squared, which is 6x, minus the second derivative is going to be 1/3 e to the 15x times 15. Now, let's simplify these fractions in here, because I know 3 goes into 15 and 3 goes into 6. So we get e to the 3x squared times 2x minus e to the 15x times 5. All right? So that is the answer we get when we do this out. Pull that back. When you take the integral, plug in your bounds, take the derivative, this is what we got. No problem. Now, the second fundamental theorem of calculus is kind of a shortcut for this integral. Okay? All right, so now, first of all, we can't use x's inside the integral because the x's are in our bounds, and you can't repeat that letter, you know, within the integral and the bounds of the functions. It wouldn't make any sense to try and do it that way. So we have different letters. It doesn't matter that we're using t's. You could use k's, you could use j's, or whatever it is, okay? But here's what the fundamental theorem of calculus says. It says integrating and taking the derivative of e to the 3t is not going to change it. That's going to be e to the 3t no matter what. But when you plug in your bound, x squared, and you get e to the 3x squared, so we're just replacing t with the x squared, we have to multiply by the derivative of the x squared, right? The bound is going to get plugged in. We're still doing the derivative of it to get 2x. So, this function stays the same. The e to the x, e to the 3t stays the same. We're just plugging in the top bound, multiplying by the derivative of that bound. Same thing with the bottom bound. You're just going to plug it in. This is going to be e to the 3 times 5x, or 15x, and then we multiply by the derivative of the bottom bound. What's the derivative of 5x? 5. Boom! We're done. We didn't really have to worry about integrating. It's just a matter of plugging in and then multiplying by the derivative of each one of those bounds. Now be careful. Both of the bounds here are functions in terms of x. If one of them was a constant, well, you would plug in that constant, but when you multiply by the derivative of that constant, you get 0. So it's kind of nice that when one of these bounds is a constant, you don't really have to worry about that term at all. And I'll show you an example like that here. So, for example, the integral from 1 to sine of x of t squared dt, we're going to take the derivative of that. I'm going to use the fundamental theorem of calculus, which means plug in the top bound. We get sine squared of x. Now I have to multiply by the derivative of that top down. The derivative of sine is cosine of x. Minus, plugging 1 would give you 1 squared times the derivative of 1, which is 0. So that bottom bound disappears completely, and we just have sine squared x times cosine of x. Okay? That's it. Done. Take a look at 2. Here, the constant is on top. So, do not change the inside function here. All we're going to do is we're going to plug in the top bound, multiply by the derivative of the top bound, minus, plug in the bottom bound, multiply by the derivative of the bottom bound. Of course, that term disappears. We end up with negative 4x cubed natural log of x to the 4th. That is the solution. And we don't actually have to worry about doing an integral. We only have to worry about these derivatives of our bounds, which come out as part of the chain rule, right? It's the chain rule that is why we had to take that derivative. Okay? Take a look at the next one. Secant stays the same. We don't change anything there because you integrate and then you take the derivative. So you're back to where you started. But we're going to plug in the top bound, multiply by the derivative of the top bound, minus, plug in the bottom bound, multiply by the derivative of the bottom bound. Done. There we go. All right. When you have derivatives of integrals where it's just x, like if it's d dx of, let's do a really easy one, integral going from 2 to x of cosine of t dt. Really easy. This is just going to be cosine of x. Its derivative is 1, so there you go. The bottom bound is going to give you a 0, right? That's just a really nice kind of easy example, okay? Good. So now you can try the fundamental theorem homework on WebWork. Stop by my office hours on Thursday or Friday, and I'll answer any questions. Thanks. Bye.